Welcome back. In the previous lecture, we saw how kets are paired with bras, and that the inner product of two kets and the inner product of two bras is given by a bra-ket product. Now, in this lecture, with the concept of an inner product at hand, we can talk about orthogonal kets, and we can talk about the length of a ket, and likewise for the bras. And we shall explore yet other consequences of the inner product. So, we have the kets that we talked about earlier for the different polarizations, and now we have their adjoint bras, and the kets we represent by those columns, or all the columns refer to the basic polarizations of vertical and horizontal, and that's what these columns mean. And then likewise, the rows that we get for the bras, they also refer to the basic vertical and horizontal polarizations, which have these simple rows of 1, 0, and 0, 1. And if we multiply a bra with a ket, well, that's an inner product of two kets, always an inner product of two bras. But once we have the concept of an inner product, we can also talk about orthogonality. So if we have a bracket which has the value 0, then the two kets are orthogonal. And also the two bras that we are talking about are orthogonal. And also, if we have an inner product, then we can take the inner product of one of those objects with itself. So for example, the inner product of the ket 1 with itself, multiplying with the bra 1, or for the same for the ket 2 that appears in our generic scalar product, inner product. Then this is a length squared of the corresponding ket or bra, and so that's something that should be positive and equal only for the null ket or the null bra. Well, which in this linear space of kets and bras is the one thing that if you add it doesn't change anything. Okay, just like the 0 and the numbers, you add it to another number, it doesn't change anything. So there is a null ket and a null bra, and they are kets and bras of length 0. Now, if we look at all the kets and bras that we have written here, all of them have length 1. So, for example, if we look at the D bracket, so we multiply the row for the bra with the column for the ket, and that product gives us 1, which is why we included these factors of square root of 2 at the beginning. Now, if I look at the product of diagonal and anti-diagonal polarization, well, that's the bra for diagonal and the column for anti-diagonal, which I read off here, and that is 0. So these are orthogonal. And likewise, V and H are orthogonal, and right-handed and left-handed circular polarization are orthogonal. So these are orthogonal, and these are orthogonal, and also these are orthogonal. and all of them are normalized. So remember, we are talking about a polarization qubit, where we have measurements that have one of two outcomes. It's a binary alternative. And this orthogonality in the formalism just expresses that physically vertical polarization and horizontal polarization cannot be mistaken. So if it's vertically polarized, it's certainly not horizontally polarized. If it's diagonally polarized, it's certainly not anti-diagonal polarized. If it's right-handed circular polarization, that's certainly not left-handed circular polarization. So this physical absolute distinguishability between vertical and horizontal, diagonal, anti-diagonal, right-handed, left-handed in the formalism is expressed by the orthogonality of the corresponding kets and bras. But there's one more thing. And for that, let's just combine things that we have already noticed. Okay, so I have the generic ket, and I write it as vertical times alpha plus horizontal times beta. Now the alpha, well, that's the bracket of the vertical bra and the generic ket. And the beta, that's the bracket of the horizontal bra and the generic ket. So if I now write this in this way, I take the product of ket vertical bra vertical, the product of ket horizontal bra horizontal, and then I multiply the sum of these ket bra products with the generic ket. Well, that's just a different way of reading this, because the v ket times the bra, the generic bra, that's just this bracket that appears here, and the h bra and the generic ket, that's just this bracket that appears here. But here we have written the generic ket is equal to something times the generic ket. So this something is the identity or the unity. And what would be the numerical symbol for such a ket bra or this ket bra and the sum of them? Well, let's see. If we take the ket v and the bra v and we go to their numerical representations, then we have the column 1, 0, and we have the row 1, 0, and that gives us the matrix 1, 0, 0, 0, which is the matrix for V selection. And if I take the horizontal ket and the horizontal bra, then the corresponding columns and rows are 0, 1 and 0, 1, and the product is the matrix for H selection that we have seen earlier. And their sum well, that's represented by the sum of these, and that's the 1, 0, 0, 1. So that's the 2 by 2 unit matrix, which describes, as we said, doing nothing. And now in this formalism, it just tells us that I can decompose the identity, the unity, in terms of vertical and horizontal polarization. Well, that's what we have been saying all along. You give me a generic ket, I can write it as a linear combination of vertical and horizontal, whatever that ket is, which mathematically speaking means that the vertical and the horizontal polarization are complete. Okay? And so what we have here is, mathematically speaking, a completeness relation. So the sum of the ket-bra product of vertical and vertical plus the ket-bra product of horizontal horizontal which by themselves are described by these very simple matrices, that sum is the identity for which I just write 1, just like the identity for multiplication in other contexts is denoted by the symbol 1. When we talk about matrices, we tend to indicate the size of the matrix. So this is the 2 by 2 unit matrix. But over here we have an abstract identity for the kets and the brass. So we don't indicate something like 2 here. Okay, so this is the completeness relation for vertical and horizontal. But of course, there is also a completeness relation for the other polarizations. So, as we have seen, we can also write any generic ket as a linear combination of diagonal and anti-diagonal, or a linear combination of right-handed and left-handed. And since these are orthogonal and these are orthogonal, just like V and H are orthogonal, we must have in the corresponding statements here. So we will have diagonal ket bra plus anti-diagonal ket bra equal to the identity, and also the right-handed ket bra plus the left-handed ket bra. They will add up to the identity. Because, once more, whether we choose vertical horizontal as our basic alternative, or we choose diagonal anti-diagonal as our basic alternative, or we choose right-handed left-handed as our basic alternative, they are all on equal footing. So what is true for one choice must be true for the other choices. In summary, the notions of normalized kets and bras, those with unit length, and of orthogonal kets and bras result as usual from the inner product. For each pair of normalized orthogonal kets and bras, we have a completeness relation, a sum of ket products. In the next lecture, we will look at other kinds of ket products.